And I'll have it on where's next to that orange laptop. Who's going to be seen? But if we don't hear you, if we only hear you, that's good. Just speak nice and loud. But we're going.
All right, good afternoon. We're going to be doing a talk on rapidly prototyping machine learning solutions, and this is a continuation of our talk we did at DerbyCon last year, where we developed a video game anti-cheat solution using machine learning. So with that, next slide.
It's on Mac, I don't know how to do that. See, you don't either.
I don't either, yeah. So there's our game talk. Oh, don't touch it.
I don't even know why I touched it.
Don't touch. All right, so my name is Jason Montgomery. I'm a principal researcher at Veracode. I work on the static analysis team, and my job is to bring on new frameworks and new libraries into our static analysis platforms so that we can scan developer code for weaknesses and vulnerabilities. I also used to teach for SANS and their application security. I helped develop the .NET course. And been a developer for about 15 years. Well, really since I was 9, but professionally since I was about 18. So, yeah.
I'm Ryan Seavey. I work for HB Enterprise Security Services. I'm on their threat and vulnerability management team, along with their DIS team, which does a bunch of incident response. Jason and I we have a video game company, which is basically just a giant black hole for our money. Don't ever get involved in that industry, I swear to God.
It's expensive.
And I also do a bunch of research now in machine learning and other areas. So we were just going to take our DerbyCon talk and just find a YouTube video and just put it up here. I don't know. I guess we'll see what that do.
That might have been wrong. It's a patch. So we're going to continue basically kind of the lessons learned from that and why we're actually probably not going to continue in the video game industry, mainly because they don't care. And it just seems like a waste of time where we'll probably find solutions that people could use in our field more readily. So we did a little more analysis. We learned some new tools that we brought into the talk as well, and then how we transitioned to other applications of machine learning.
So originally when we were looking at the video game stuff, this is kind of what we thought would be important to them, but like we just said, they really don't care about much of anything. So, but you know, there's obviously a lot of parallels between this and probably what a lot of people in this room do every day, especially in application security and things like that. I mean, when you look at the two, there's a lot of common similarities, especially when you're looking at the basic problem of how do you detect a cheater, right? You're either cheating or you're not cheating. We kind of apply that same logic now with looking at network traffic. So later on, we'll go through a IDS log, and we basically are asking machine learning to identify the traffic as either being normal, port scan, whatever. So we're asking it kind of the same question: is the traffic normal, or is it something else? And if it is something else, then what is it?
Yeah, when we originally looked at the video game industry, it's kind of interesting. We left some of the slides in just to kind of give you some background. There is a similar market as there in the cheating landscape as there is in the sort of network security landscape as well. You've got the makers, the distributors, and the users of that. Those cheats, and it's not unlike how network malware writers and things like that function too, selling their malware to people as well. So it's a similar situation.
We should have just taken that last slide and put Kevin Mitnick in the background now. So just to go over real quickly, I mean, the cheating economy, it was obviously something that does quite well for the people who are developing them. Again, it was a little bit surprising that not that many companies seem to really want to invest in the anti-cheat tech. But kind of as we talk about, it's not that surprising when you're looking at how video game companies make their money, right? So they're in the business of selling software. If we ban a person who's using our software, but they really like our game, they're probably going to go out and buy it again. So it's just like this conflict of interest thing almost. I mean, if you're the person making Counter-Strike, which is what we did our initial research off of, so you ban the account, then you have a Steam sale, and now you can go pick it up for $8. I guarantee you they're just going to go out and buy it again. Like, it's not that detrimental to them.
Yeah, they're already paying, what, $12 to $20 a month for the cheat? So it's $8.
Yep, and also it's interesting to note that these companies, such as Valve, they have the technology now where they could ban people by hardware ID, but it's a little bit more difficult than, you know, just going out and making a new Steam account. They were playing around with that, and then they decided not to do that. So you can draw your own conclusions on why that may or may not have happened. But when we look at the anti-cheat examples and the systems that are out there, so you have your signature-based stuff, which is obviously very similar to what we have today with AV and things like that. The server stuff, which is more statistical-based, and then they have the human stuff, which is something called Valve's Overwatch, and there's other things, but it's basically where people sit there and they watch these demos of people cheating, and they say if they are cheating or they're not cheating.
So there was an interesting dialogue about this on Reddit, where Gabe jumped in on basically saying to all the video game players, you really need to trust us. And this was based on the invasiveness of their cheat detection and prevention software called VAC, or Valve Anti-Cheat. I'll just read a few of the blurbs here. It says, for most cheat developers, social engineering might be a cheaper way to attack the system than continuing the code arms race, which means that there will be more Reddit posts trying to cast VAC in a sinister light. And Gabe's trying to defend what they do with this. The specific VAC test with a specific round of cheats was effective for 13 days, which is fairly typical. So they build cheat detection, it works 13 days, and they have to go back to the drawing board and then develop a new anti-cheat, which isn't awesome. 13 days of coverage is really not what I would consider a success story.
In this particular scenario, just to give some background, this was when people were up in arms when they discovered that Valve Anti-Cheat was sending back DNS information to Valve. Gabe was basically just saying, hey, look, you can trust us, we're the good guys. But
yeah. At least they were hashing it, but still, I don't think it was, it's debatable whether that was enough. And then the last quote, our response is to make it clear what we were actually doing and why, with enough transparency that people can make their own judgments as to whether or not we're trustworthy. And of course, he comes out and says that they're being transparent only after they were caught. So I don't really call that transparency either. And then we have FireEye, the Senior Vice President for Information Security at Symantec, Brian Dye, talking about antivirus, which is the signature-based detection, which is what Valve Anti-Cheat is. And he's saying 82% of all malware it detects stays active for a mere hour, and 70% of threats only surface once, as malware authors rapidly change their software to skirt detection from traditional antivirus solutions. Function signature-based AV serve has become more akin to ghost hunting than threat detection and prevention. So the point was antivirus is dead, which I think most of us in the field already have been well aware of for a while now.
So this is just, now we look at what these anti-cheats are doing, which I really kind of expected more people in this industry to be up in arms about. Because look, if I want to go play a video game, I don't think that you guys need to sit there and monitor my RAM, my processor, what browser tabs I have open, what my DNS looks like. And their end-user license agreements all say that they can do this, but on the same token, number one, a lot of people don't read that, which I guess you can say shame on them. But on the other token, is it really worth it as an end consumer for companies to get away with this? I mean, number one, even if they are doing it for legitimate purposes, what's to say that some malicious actor isn't inside of Blizzard's network looking at all this, right?
Once they have the data, it can get exposed, so that's not awesome. So we just put a few anti-license agreements in here. We can skip over these quickly. I think they basically say they can do whatever they want on your computer anytime, monitor you, essentially. So
just some more same stuff. So when we look at how the actual cheats are being distributed and how these are working and everything, they do have their own DRM system, right? So you have to have an account to go on there, and it basically checks to make sure that you have your active license, and then it will send you down the most updated version. Obviously, we don't have the most updated version since the anti-cheat's constantly getting updated, you're probably going to get detected and then banned. So below is just some of the traffic that we captured, and it kind of shows what's getting downloaded after you've been authenticated. And then we look more in depth into those files, and they're doing a lot more than just letting you see through walls.
Yeah, there's we have a strong sense that there's malware inside the cheating software as well, on top of the actual anti-cheat, which kind of makes sense when you think about it.
Right. I mean, basically, where they're operating, where they're living, they basically have to be rootkits. That's how they can avoid what Valve is doing to kind of detect the cheaters. So if they're running there, that means that Valve has to also get there, and it's a big giant cat and mouse game that I think in the end the only person who's really losing is the end user. So we're going to skip our cheating video so that we can get into some more of the actual IDS log analysis. But basically, we have a video and it shows us cheating, and we never got banned. The account's still not banned, so the conclusion was that that really doesn't work all that well.
Yeah, if you use a good cheat, use it properly, Hack does not detect that it exists.
All right, so now let's start making more parallels. So our problem with this was, like I said at the beginning, we wanted to make a anti-cheat system using machine learning because the problem was, how do we classify people, right? Are they cheating or are they not cheating? So, like, our proposed solution with all this was we used machine learning and it was going to work. And then we kind of said, dirty con, look, we just started, we know that our data set isn't exactly perfect. And then we find out, I think 2 months after we gave our talk, that 20 to 30% of the data that we were using to train the model with the pro players, or the people that we believe were not cheating, were people who were actually cheating.
So 30% of the professionals were cheating that came out, which isn't surprising when you look at how well the cheats work and how poorly VAC does to ban them.
So let's talk a little bit about getting data. Right, because if you're going to sit there and if you're going to try and start doing machine learning on maybe your own network, you're going to need to start gathering data from somewhere. So in our case, when we're doing the anti-cheat stuff, we had to go out and we use, well, basically we wrote scripts that would crawl sites and it would pull down data. If you want to do this with your own network, probably start looking at IDS logs would be a great place to start. Beyond that, I mean, if you have SIM, any place that's sort of gathering logs.
And the more data, the better. You really want to have a very large data set. The more you have, the better that the system's going to work for you. So make sure you get a lot of data. The other thing you want to really make sure you do is choose the features well, which we'll talk about later a little bit.
So like we said, we definitely knew that we had some issues, and even when you look at IDS data, whatever it might be, you're going to have similar issues. You're just going to have weird stuff that's out there. So the best way to kind of deal with this is just filter it out. When we were doing it, we saw players that had these stats that were astronomically impossible. So they were either doing something with the API to alter the stats, or they were just not relevant because it was going to skew everything that we were trying to do.
Yeah, the other thing we really wanted to see was a lot of the features that they had internally, but they would not make available to us publicly. Okay, so for the anti-cheat system we did, we decided there was a classification problem. There's really two types. This was classification, meaning it started cheating or not cheating. It's kind of a binary situation. And we decided to use supervised learning, which essentially means we look at all the data we have, and then we also have an answer in that data set that already flags the user because we used Valve's anti-cheat data. So there was already a flag whether they had been VAC banned, right? So we took all the statistics for the game, you know, their accuracy on pretty much in every weapon type, their accuracy on their, I think, total wins per hour, any sort of heuristic stat we could grab that would sort of give us an indicator of cheating. And then we also took the VAC ban flag and fed that in. And what that did was it said, hey, we have all this data, and we give the machine learning algorithm the answer. And all these people are VAC banned, right? So we don't really have to write any code. We just really have to load all the data in and give it the answer. And then it looks at all that data and runs a lot of algorithms. some calculus, statistical analysis, things like that, and it spits out a model that then you can feed one record of data to, and it'll put it in one of those two categories, cheating, not cheating, which is pretty cool when you think about it, because normally you typically have to go through and write probably an extensive statistical analysis engine yourself. But with machine learning, it builds that model automatically with pretty high accuracy in many cases, as we'll see. Even with our bad data, we got pretty high accuracy for whether the user was backbanned or not.
So like Jason was saying, when we first started this, we used supervised learning, but one thing that we just didn't have enough time before we gave our first talk was we wanted to see what would happen if we did unsupervised learning. So we now have a model for that we'll show, and that is a lot more interesting than our original model.
Yeah.
So when we were doing the first round of this, we used a boosted decision tree. And this is basically a really dumbed down version of how a decision tree works. So this is, if you go to Wikipedia, this is what they have. And it's basically, would you survive the Titanic, right? So what this is saying is if you were male, and if you're not a male, then you had a really good success rate of living. And then it looks at your age. So are you over 9.5? And then if you're over 9.5, then it looks at if your siblings and spouse. So if you had basically kids.
If your family was with you.
If you had family that was with you and it was 2.5 or more, then you had the highest chance of surviving from that decision tree.
Yeah, and what's cool about this is no one wrote the code to do this decision tree. The data of who lived and who died and all the stats about those people were fed into the model, and the computer figured out how to make this decision tree for us. So we didn't have, no one has to write this code. And you could use a different data set on a different vote and figure out a different decision tree without having to write anything or update anything. You just need to build a new model. So yeah, this talks about unsupervised learning. And this is essentially, so the decision tree, we give it an answer, and that's supervised. We say, we know these users are backbanned. In this situation, we throw all the data at the algorithm and let it figure out where the clusters are. So it's going to look and say, all of these data points, all these records seem to be grouped in a similar category. And it allows us to find hidden structures and relationships within that data set that if we were just looking at it as humans, we may not be able to see because there's just too much data to sift through. Right? So this is how Google classifies its news, right? What category it lives in. So the way Google figures out, there's not a human sitting there going, that's a politics story, that's a technology story, right? They're not doing that at all. They have a machine learning model that scans the article, extracts the features, and then clusters it in one of those categories. And when your news comes up, they just show up in the right category based on the classification that it determines. So we decided that since the backbanned flag was not really, there were people who never even really played because they used to cheat wrong and they got banned immediately. Well, that's going to throw our stats off, right? Because all their stats are bad. So when we look at our model and the graphs of our model for the decision tree with the backbanned flag, where we thought we had an answer, that really didn't end up being a very clean model. It still was 83% accurate, though, which is really interesting as to whether they were backbanned or not. It may not have been accurate as to if they were always cheating or how they were cheating. The way this model worked, we had a much higher chance. Oh, and here's a little chart that shows you how this works. So it's kind of just figuring out where clusters live, and it'll kind of draw a line, and you'll have some outliers, but this is a linear support vector machine. It's decision boundary, right? So one side or the other is kind of, and then the computer sort of figures out, this is an easy example, which side of the line they live on. And then we did it on a bunch of our features, and we got a lot. You can just, we'll show you some scatter graphs here soon.
Yeah, we'll actually do that now. So now's our demo.
Okay, yeah, good.
Get over here and work this Mac. All right. So what we're going to do, if Jim Kessler was here, I'd have him do it, but I don't know where he is.
I got to turn off my display mirroring. Bear with me 1 second.
So this is called Weka, and it's a free tool that you can use to kind of start messing around. So what we will start with is, how about we start with the cheat stuff?
Okay, you got it up now? Good.
Yeah, this is the IDS one.
Okay, so let me just close this down. So Weka is a really cool tool. that, sorry, escape out of that demo.
You can get this right.
Yeah, I think you can find it. All right, so WebKit is a free tool, and it's switched screens on me. This is awesome. Is it on there now? Okay. Okay. Okay, so WebKit is a free tool that has a lot of stuff you can prototype locally. When we did the machine learning the first time, we used the Azure platform, cloud platform. This was nice because it gave us a lot more tools to sort of visibly look at our data. So, just the screens are mirrored, so it looks really confusing. Okay. So we pulled our data into this tool. Okay. So this is just a CSV file that essentially has our features from the Steam Valve API. It's got a win ratio, and we also did some math to come up with statistics or heuristics that matter, like a win ratio, the total accuracy in the game, kill to death ratio, total wins per hour, and those show up here on the left. And then on the right, you can see sort of a snapshot of that data, how many distinct records there are, whether the type is nominal or real, what kind of data type it is. You can immediately go in and start to visualize the data in the tool and with different scatter plots to sort of screen out data, to cut out outliers, things like that. Should we do it?
I don't want to do a classify.
Okay. So we're going to do a...
Let's do a percent splits in this top fast.
Okay. So we tell it where the answer lives. So there's a drop down here you can see that says right here, and you can pick which column has the answer to train the model with. So we put the backband model, is a nominal flag that's either 1 or 0. 1, they're cheating, 0, they're not. And then we're going to choose which algorithm we want to use. And we use the J48 decision tree. And I'll just hit start. Oh, I didn't exclude the Steam ID. Hold on 1 second. We also have to remove the Steam ID because that is not interesting data before we run that. Also, it does give you some of you can see the band and not band. The red is the band for each category. So it'll sort of graph each one of those automatically for you very quickly. All right, so we're going to change, oops. All right. And then we're going to split the data, 66% we'll use to train the model, the other 33% we're going to use to test the model's validity. So that quickly, we have a very complicated J48 decision tree, which is essentially if-then logic.
Your Titanic example that we had earlier, this is the decision tree that it used to determine whether or not someone should be backbanned. As you can tell, it's a little bit more complicated, and you can actually visualize that as well in Weka, which is kind of cool.
Yeah. And also you can see the true positive rate, the false positive rate, what precision, recall the area under the curve, and this has about a 76% accuracy. And then we have like a confusion matrix, which shows false positives versus true positives and things like that. So we very quickly could get an answer. And with the one we tuned, this isn't really tuned, but the one we tuned in Azure, it had a 83 or 87% accuracy.
Like 86% in Azure. So this was just, like I said, we just loaded this up just now. Ran it for the first time. We don't have any filters going on or anything. It's relatively accurate.
Yeah, 75% isn't bad for basically no work. We didn't spend that much time. Other than it took us more time to retrieve the data than it did to get the answer, the decision tree built. Now, again, that's not an awesome number either, though. You wouldn't want to start banning players with just a 70% accuracy. You're going to piss off a lot of people. And then to show an unclassified one, we're going to show how we can cluster these. Okay, and we're going to ignore the answer field. So we're going to say, don't pay any attention to the answer when you do this, build these clusters, because we don't want to give it any clues as to what we think We want it to figure it out. We don't want to tell it the answer. And then we're going to use a k-means. I like how my... Oh, there, the simple k-means. Okay. And we'll run that, and you can see it says, these are the columns we used, and then it tells you which ones it ignores, and then it essentially has our model built already. So then we can go and visualize our cluster assignments, and this is really the sort of cool part where we get to look and visually sort of validate.
So this is all of the data, and the blues and the reds are basically the two ways that it's classifying everything. But what's really interesting about this, and what's kind of cool, is you can click on any of the X's, and it will show you data for why that X is there. So
yeah, I click on an X and I get what cluster it showed up in and all the stats. So we can kind of eyeball our solution and say, yes, the items in the red were not cheating, the items in the blue were cheating. We can kind of see how it's nicely split down the middle. And then for each metric, right, they're sort of split in the same way, and we can see the clusters. So we probably would want, if we implemented this, we would want to probably have sort of a no man's zone in the middle that we wouldn't want to classify people at. And then if it was over a certain threshold, we would just start banning those people. I think, I don't have anything else to say about that.
no, so like I said, this is just a nice example, and this is just data that we're familiar with. Because like I said, we started doing this with the anti-cheat stuff. Then just recently we started doing the IDS, more the InfoSec piece of this. So why don't we load up the IDS data now, since I think people will find that a lot more interesting maybe than our cheating stuff. So what this file is, it's just some sample data that Microsoft put out there on the web that they collected from a bunch of different IDS appliances. And it has basically the attributes of what the traffic looks like. So once it's loaded, we'll kind of go through that briefly. All right, so you guys can see that we have duration, type. Later on, it shows like log on attempts. But then the main thing that we're trying to figure out here is class. So inside of class, we have, basically we'll have normal, and then we can start going down. I mean, you'll see things like InMap, it'll classify that as that. Just a bunch of different stuff right now that it's going to figure out. So, train it.
Yes, sir.
So we're going to do the same thing that we did with the cheats. The accuracy is going to be a lot better. I think this spits out somewhere around 99.26% accuracy. Yeah. So we're going to use the exact same tree. We're going to use the J48. And now it's going to build our model in 22 seconds.
Oh, I did 10-fold cross-validation. It's going to take a little longer. We stopped it.
Yeah, and just, you're eventually going to want to do the folds, but since we don't want to sit here for like 5 minutes while it does it, we'll just do the splits, which again, when we're splitting, we're taking 66% of the data, and then we're going to try the remaining, or we're going to test it against that, so.
You get the dancing bird when it's working.
You do.
Yeah, this is all free. It's kind of nice. You can just load it up. And there's a ton of data sets online you can download and play with to sort of get familiar with how this works and the type of features you may want to choose. So there we go. So there's our big decision tree that it built.
It'll make the matrix here in a second.
So we'll flip through that while it's building the confusion matrix. So now it's going through the test. How valid was it? So it trained the model with 66% of the data. Now it's going to go back and test it with a totally different set of data it's never seen. And that's how really you can only tell if it's working, is you have to use that cross-validation. Because if you test the same data you trained with, you'll get like 100% accuracy every time because, well, for obvious reasons, I think. So here's our confusion matrix, and this is kind of a truth table that essentially tells us how many were correctly identified across each classification. So IP sweep, normal traffic, a Smurf attack, whether it's an FTP write or a rootkit, things like that.
And you read it diagonally. I get that. And don't look at it like an Excel spreadsheet, it's a matrix. So.
Yeah, so A, normal, 22,841 were classified as normal correctly. Now, if you go over to the right of it in the B column, you'll see that 2 were incorrectly identified as Neptune, right? So that's pretty accurate. So if I was going to, go through these logs and I wanted to quickly flag data without having to pour through every single record, I could run it through here, and this just helps me narrow into which ones I may need to look at. So if you miss a couple, you're going to miss a couple as a human looking at the logs anyway. But I think we're going to get a lot more accuracy here. So if you look at Neptune, BB, where it's 14,050 here, and then I think one was misclassified as Satan, right? There's three of the network records were identified as the wrong one. And right on down, we have mostly normal traffic, and then it's sort of descending in order of prevalence in the log. So it's kind of cool how quickly it was able to sort of come up with a classification engine for network traffic.
Right, and in the real world, you're going to have a lot more things that the traffic can be classified as.
Yeah,
this is just the beginning of what we're looking at doing as far as what your network traffic can spit out. It's also interesting so if you're on the offensive side of the house, why do you guys care about this? Well, you guys should probably figure out why and how this is working, because I guarantee you this is all going to be coming, and I don't know how quickly it's going to be deployed out there, but you're going to need to know how to figure out how to beat this, right? So it's relatively easy, I would say, to defeat the humans today, because let's face it, a lot of people don't sit there at the SOC and correctly identify the traffic. I mean, I've been on engagements just recently where we were in there and their SOC kept pinging us, but it wasn't us. We were never the actors. So they never found us. They found other stuff, but they were never looking at the right place, right? So they even knew that we were doing the testing. But if you had logs like this, if you had machine learning in place that was actively kind of scanning what's going on in your network and evaluating it, it would probably help out the analysts quite a bit, because now they can say, okay, hey, look, here's the stuff that came in either from today or from this week, and we're seeing a bunch of in-map scans. Why is that?
So I just ran this through a cluster to see how, because sometimes you don't have the answer, sometimes you do. But if you can train it, I think, with network one with the answers, that means you've gone through the data, you've gone ahead and classified it as accurately as you possibly can. So there's an upfront cost to getting the data set good. But once you do and have that, you can run it. This one is I'm going to run it through a cluster to see if it can unsupervised, where we don't give it the answer, to see if it could come up with what it's finding. Looks like it's done. Yeah, in this case, you'll see it's not very good. So we have 37% and 63%, not awesome. But if we go, only 2 clusters.
If we look at the visualization, though, that's where there's even more of a, okay, so why does this look like this, right? So when we start looking at how the machine learning is viewing at this, and it's all just trying to cluster things together, because obviously certain network traffic is just going to look similar, and that's what this is really doing at the end of the day. It's just trying to find the clusters of, hey, is this a port scan? Is this an in-map scan? What is this? So it actually does distinguish the difference between in-map and port scanning. But when we're looking at this, so that's a good example, right? All this stuff up here is probably going to be port scans.
And I think what this illustrates too is even if you don't do machine learning, just visualizing your data is actually huge. Like you can just see certain patterns in the traffic already, right, when you graph it. Different. Yeah, you have to get off that slide.
So what we did was we just clicked on one of the points, right? So it was up there at the top, and it obviously looks like when you just visualize it with the naked eye, you can tell, hey, look, why is this cluster here? And then going through it and looking at all these points, which is what happened when you click on that, they all show up as a class of port sweep, right? And then as you kind of start going through this data, you'll start seeing similarities of where it classifies other things too. So if you have a bunch of rootkits on there, depending on how that traffic is going around your network, it'll be able to classify that. I mean, this, I think in our opinion, is definitely where things start needing to go, right? Because let's face it, there's tons of data out there now. I mean, especially if you're a Fortune 500 company with 200,000 employees, your logs are going to be quite massive. And
yeah, and this it seems like the only way you're really going to get a handle on that data. And I suspect a lot of the industry is going to head this way in their products, hopefully. Yeah.
So this was an example of Weka. It's really, really good at kind of using smaller sets of data. The data sets that we both use for both of these, I think, contain probably about, I don't know, I think 20,000 rows sound about right.
Yeah. And there's a workflow builder, so you can actually build a workflow, and then at some point it generates Java code for you. But maybe you want to talk about H2O, or is that?
Yeah, so like I said, Weka's really good at doing little stuff quickly. But as soon as you start to kind of do your folds, and if you want to do 10 folds, it's going to take a little bit more time. There's another platform out there called H2O, which is more optimized for large data sets, and it integrates with some of the massive databases that are already out there. So if you're dealing with that kind of data, definitely go down H2O. It's also another free tool. And then the final tool that we kind of have been messing around with and we actually started with was Microsoft's Machine Learning Studio, which is really, really good for deployment. So if you go out and you build these models in Weka, and now you're like, well, okay, great. So I have this model and it sits here on my desktop. Why do I care? I mean, great, I can look at it, whatever. How do I feed stuff into it? That's maybe where you might want to use Machine Learning Studio, because you can basically just draw out your model, and then it took us, what, like 2 days to make a web service?
Oh, yeah.
So this is what Machine Learning Studio looks like. It's a lot more graphical. I mean, you just basically make your workflow, and it kind of makes it so that you can't screw up.
Yeah, we did a lot of data normalization. There's no code here. You can write R code, which is kind of the language you want to use if you want to do machine learning programming. So it has workflow elements that support that language, but we just, essentially, I think a span of 2 weeks, built this model and got it to about 80-something% accurate on our CSGO stats.
And what this allows you to do, again, from a deployment standpoint, is we now make this as a web service. Someone can go out there, you input the data, and then it will run it against the model. So maybe our deployment solution with what we wanted to do with the IDS stuff is maybe we wanted people to be able to upload logs to us. And then it would instantly analyze the log and spit back, here's your confusion matrix, or here's your answer, here's your classifications.
Yeah, so this circle here, I just clicked and said make web service. And then you give it a row of data with a JSON call, and it gives you the answer whether they were cheating or not. It was really like 2 steps to generate a web service. It's really, really slick. And then we can go down to the model where it's hard to see on this overhead, I realize, but we can look at the model scores, and it'll give us these stats in Azure. It does not have the really cool charts, right, that Weka did, which is why we like Weka for, I think, doing a lot of the preliminary research.
So Azure, you're supposed to be able to do the charts, and you can do them with R, and we tried to do a bunch of them with R, but they weren't very good. I mean, Weka makes definitely better.
I'd rather not have to write code if I don't. I'd rather spend my time elsewhere. I don't mind writing code. I like it, but not on frivolous things that something can do out of that. Back to the slide. Okay, so here we just sort of wrap up why we're probably not going to pursue the video game line. We're going to work more on network security, and I'd like to do some static analysis, machine learning static analysis. My company does that some internally as well on some of our platforms too. But I'd like to do some research with some different tools and show other people what they can gain from it. So some applications. So sort of thinking about this. Is there any questions so far on what we're talking about here before we jump into some more applications? No? Okay. Spam filtering is probably the first place all of us saw this. Bayesian analysis. This is machine learning or AI, are the things I call that. There's network traffic identification, data loss prevention. It could be used for that to sort of identify You also don't have to do machine learning to do some of these things either, but these might be some good applications. Or malicious traffic or intrusions, identifying humans versus machines. And I think the new reCAPTCHA project from Google is now using machine learning to, they're not giving you as complex CAPTCHAs to type in, they're just giving you like a 3-digit number, but they're looking at a lot of the heuristics as to how you type that in, and they're capturing data around that to see if whether you're a human or a machine. Static binary analysis, looking at PE headers, how code's made up, API calls, and when you know things are malicious, and then you can run binaries that you don't know, and it will classify as maybe potentially malicious or not. And then dynamic behavioral analysis, kind of like your dynamic website analysis to see if a site has potential vulnerabilities or things like that.
Yeah, and while not an application for InfoSec, since we are in a hospital, we should probably mention that if you start researching machine learning, one of the more famous things that you do is look at how you can look at cancer data and the size of tumors. And then machine learning will classify whether it's cancerous tumor or non.
Yeah, and then they use that now
size and a bunch of other stuff. Yeah. So
that's how they diagnose now some things too. So you'll see it in neuroscience, in pretty much any field really now. Sort of on the, I don't know if it's cutting edge, unless you consider cutting edge the last 20 years. But it's getting more prevalent as our systems get more powerful, and now that we can leverage cloud computing, you can have a lot more CPU power to sort of churn through, and the big data sort of databases will help you get through that data. Whereas if you had that many record sets 10 years ago, I don't think anyone would have the computing power to do it efficiently to make it practical.
Here's a couple tools and where you can go to get them. Like I said, all these, well, the first two are free. Azure has, if you have I think if you have a subscription through MSDN, you can use it for some amount of time for free. After that, you have to start paying. But
I think you can anybody could do 30 days, I think, without cost. And then it's experiment time, so if your experiments don't run that long, you're not going to, you could prototype stuff initially without paying, and I don't think it was that expensive if it's not getting if you're not hammering the APIs anyway.
So we have, why don't we do another with Weka? Why don't we show them a tree, even though it's going to look horrible?
Show them what?
The actual decision tree.
Oh, that, yeah. All right.
So what we were talking about earlier with Weka is how you can actually have it output the decision trees, and it will show you how it ends up classifying it on a nice visual. And I say nice visual loosely because this is going to look like a giant cluster of nothing. It doesn't fit the screen very well.
No, it's not great. All right, so that was fast. Oh, what did I do wrong? Oh, I didn't change it to J48. Okay, let me pick the correct. All right.
Now you can see the dancing bird. But while we do this, if there's any questions, we'd be more than happy to answer them.
And the disclaimer, neither of us are.
We don't have PhDs.
We don't have PhDs. We're really not math buffs either. We took the class, Stanford class, on Coursera and got through most. To the part where he said you now know more than most people in Silicon Valley, and we were like, that's a good place to stop. Yeah.
You mentioned using J48 multiple times. Did you use multiple algorithms, and what was the variance between them?
Yeah, so we
used a 2-class decision tree, I think.
Yeah, we used
Azure that got better accuracy than the J48. I don't know if we have the variance right off.
I don't. Also, the other thing with Azure is that you're a little limited in what you can use and what you can't use.
Yeah.
And it's also still in beta, I believe. But yeah, we use basically every single kind of tree that they offer. Boosted decision tree was what we got the best results out of, and that was after tuning it for quite a while. And like we said, we were using J48 without any tuning, so we're not going in there and telling it how many, what do they call trees, and how many trees to kind of use and everything else like that.
Yeah.
So this But this is basically how it visualizes all the data when you're done with your tree. So as you can tell, it's just kind of all over the place.
Yeah, not really useful to look at, but
You can zoom in, and it does a really bad job at that too.
it is Java-based. Let's be honest. But yeah, and what's nice about this is we actually just ran through every model that made sense. So we would do a forest versus decision tree. We would do supervised, unsupervised. And we just keep looking at the AOC, the area under the curve, and some of the precision and false positives, true positives, and the false negative results to see which one did perform better. So it allows you to quickly prototype that. There's also features in there that help you tune your model and how it generates the model. So you can go to Azure and say, I don't know how to set up how many trees to use or how to structure that tree. So you can go into Azure and run your data through this model. And there's a similar, in the select attributes tab here, it'll help you pick which attributes in your data set you want to use as features. So there's a lot more to this. We're just sort of really at a high level now, just kind of introducing the topic. And we're still learning as we go, as it is new to us too.
But yeah, I mean, again, just look at this matrix. I mean, if you look over here, it has the buffer overflow. I mean, you go down here and you see 4. I would think that someone might want to investigate what's going on there. I don't know. I mean, it's kind of nice because you can start finding needles in the haystack quickly. This mic sucks.
Yeah, I think you have to hold it
Up to my phone.
you have to hold it like a rock star.
Oh my god.
Yeah, so I guess that's it on this talk. Any other questions?
Yeah, go ahead.
You mentioned and showed some pictures of visualizing some of this data. Has anyone done anything where you do auditory analysis on it? Listen to the data.
Certainly, I have heard of such things. I know some people will pipe their logs to the audio as they are collecting. I've heard of this. And I think that was like 15 years ago that I heard of that. And I do know that they start to do weird things when a lot of things change, like you get used to the sound. So I've heard of that. I don't know. There's probably something to do there. I don't know. It's interesting, at least. Have you heard anything else, or no? Okay. Wasn't sure if I missed out on something. Cool. Yeah. Yeah. There is a lot on YouTube. Of course, it's a good Weka tutorials on YouTube, so I would recommend just going to YouTube and look up Weka there. There's a Weka course you can buy. We haven't
It's
looked
like
at that.
$40 to buy a course.
Which cost of a book, really. That's probably worth it.
Or you can just go on YouTube and find a bunch of free videos
Yeah.
or whatever platform you want to use. So if you want to use Weka, I think there's 18 courses that you can just go on YouTube and start going through them. Or if you're interested in H2O, they have a bunch of course content too.
Yeah, H2O is built in for free into the platform. Right?
Yeah, H2O is actually kind of cool because if you start using that, it deploys to EC2 and things like that. It has all the scripts in there. So if you are dealing with huge amounts of data, it's all already kind of got the configuration scripts. You just deploy it to EC2 and away you go.
Yeah. So, and I think Coursera has a few other courses I've seen pop up that I haven't taken, but I'm interested in the more practical aspects. Because the course we originally took was essentially like mathematical theory, which was fine, but I'm really more interested in the practical applications of it. I mean, it's nice to know how the algorithms work, but it's more helpful for me to know just which one to pick and how to tune it than it is to really know the calculus. It was interesting, but I think practically speaking, I didn't know it as much as I thought I would.
The main takeaway that we hope that you guys have from this is don't be afraid of machine learning. Get out there and start playing with stuff and see what happens. You don't have to know calculus or be a master of statistical analysis or anything like that to get started. So there's no other questions. I guess we're done. Oh, one more.
So you mentioned a lot of, I kind of look at this from a defensive perspective, but based on what you know now, if you were trying to cheat, what lessons did you take away and how do you approach those?
Right.
So he was asking how we would take our lessons learned and now approach cheating. So the first thing that I would do personally is I would never ever use an aimbot, because that is just obviously your accuracy is going to spike through the roof. It's very, very obvious, which is very easy to detect. And even valve anti-cheat can kind of start to detect that a little bit more. But from Valve's position, they have to match it to a signature, so they know for 100% certainty that yes, there's something on your machine that's running, and now we're going to ban you. So if you don't use the aimbot, you're going to be far ahead. If you just kind of use, if you just see through walls, you're going to have maybe some more inflated stats, but I think that's a little bit easier to hide.
Yeah. Were you curious about how to use machine learning to go on the offensive and hack stuff? Or was it?
What parts of the model are, I mean, not necessarily specific tools, but like what parts of the model do you see you could attack? Like, is building an aimbot that hits 90% of the time,
Sure.
100% of the time going to be a lot more effective?
Yes.
Yep. If you start building in, let's say that you have an aimbot, and it's only going to make you hit every 1 out of 4 shots, right? Well, then that's going to kind of start messing with the machine learning algorithm a little bit, because now you're missing 75%, and you're only hitting 25%, which is probably more in line with what the masses are doing.
Yeah.
So, I mean, you could apply the same thing to network security, right?
Yeah.
So if people really want to get knowledgeable about machine learning, predictive analysis, the electronic data discovery industry has been using it for years.
Yeah.
And it's really important to understand the algorithms vis-a-vis what you're trying to find. I mean, you don't have to know the calculus, but you do have to understand the algorithms and the different weighting factors they use. Because in litigation evidence, accuracy is, I mean, you can't tell the judge, oh yeah, we did this and we had 86% accuracy, let's go out of court. So those, and you don't really, there's lots, you can just Google electronic data discovery and predictive analysis is what they call it in the EDD industry. And there's all kinds of tutorials and blogs and things to learn about how to set up what's really important. They call it the syllabus. So you say laws.
Sure.
But in that industry, it's known as the syllabus. You have to train the tool to find the words that you're looking for and the paragraphs that you're looking for. So it's the same concept.
Cool. Thanks. Yeah.
Yeah, and we didn't get enough time to actually start going into the tuning of the trees and all that. But, you already got 15 minutes, so.
I mean, the concept of tuning is the same in that industry. They just use different words.
Yeah.
They're lawyers.
Awesome.
Just curiosity with the aimbot data. Since you only need to cheat on the shots that matter, would I throw off the detection if I bury a mag in the wall?
If you do what?
Bury a mag, do a mag dump in the wall, throw my accuracy.
Well, you can actually kill people through walls, it turns out.
Right, but I think he's saying if you just start at spawn. But yes, so that would work. But then I would argue, okay, so if you're starting a matchup and every single round you're unloading your clip into the wall, someone's going to be like, okay, what the hell are you doing, right? Like, no one does it. That's also going to raise the flag of, well, why is this guy wasting all this ammo, right? So, I mean, there's always going to be creative ways that you can start skewing the data.
Yeah.
But, I mean, at some point in time, you're just not going to be able to defeat the machine learning, like if you tune it correctly. But a lot of the professionals, how they were getting around it was they would just they would use a trigger bot and it would only be for certain shots, right? So these guys would be at competitions, and it's actually really fascinating on how these hacks are working. They were using the Steam Workshop to go out and download them. So there's some vulnerabilities there, but that's a different talk. So. All right, well, thanks for coming, guys.
Thank you.